Some of us still struggle a little bit with piecewise. I kind of like the little circular thing. Maybe I should put the whole room in like that, like this. That would be cool, wouldn't it? That's what I'm saying. If we kind of circled like that with the board, it's kind of cool, right? Like that's your. I could do it like in groups of 3, but like that's your group. But I kind of like it. I might do that this afternoon. Huh? Calculus did this morning. They had to teach the freshmen all the chants that y'all sing at the football games or something. So they ended up not getting back to class until like 9 o'clock, so we only had 30 minutes. That's why we were late finishing up this morning. They took like the high school 101 class with all the freshmen in it, and they took like there was apparently Coach Beck and somebody, I don't know, but they had them in like the gym or something, and they stood up there and taught them all the, because all the student council people are in my first block, so they just, all right. What number are we on? 9. Y'all, I am not looking forward to this.
What? Looking forward to teaching? I think we have like a fun day. Oh, what is this? What?
This is a trig function.
What's that trig?
You should have trig. Yeah, this is, so there are 3 trig functions. This is one of them. Trigonometry. So think back to geometry. When you did sine, cosine, tangent, this is sine.
Wait, so is this called like trig function? What's the name of the function?
This is the trig function sine. That's not sine, that's sine. But we abbreviated sine, S-I-N. All right. Shy of deriving the unit circle with you and giving you those values and telling you where these things come from and explaining radians, which we will get to eventually, we're not there yet. This is going to be a memorization type deal for you right now. Okay, so I want to show you what this looks like. So this comes out to look like oscillating waves. Okay, if any of you have ever heard, maybe in science y'all talked about waves, maybe sine waves, sinusoidal waves, yeah. Okay, so this is the graph of sine x. So here's what we're going to do for your t-chart. This is going to look a little funny, okay? We're going to go, okay, remember pi from circles and diameters and radius and everything else that you have? Okay, that's the pi we're talking about, but we're going to go, as we do our graph, we are going to go by half pi's. So pi over 2, pi, and you need to take it out to 2 pi. This is 3 pi over 2, and this is 2 pi. Okay, same on this side. What is 1.5 pi's?
What is 1.5 pi? Oh, it's 3 over 2 pi. I can't.
Okay. All right. This is half pi's. Every section is a half of pi. Okay. This is pi over 2 is the same thing as 1/2 pi. Pi is the same thing as 2/2 pi. 3 pi over 2 is the same as 3/2 pi, and so on and so forth. It's just that every other one is a whole pi, yes? Are y'all following me?
We're going to say yes.
Okay.
-3 pi over 2.
Brett, could you please contain yourself?
We do -3
All right.
pi over 2.
You can, this is enough to go through. This is enough to go through. All right. You're going to take your y from -1 to 1. It never goes above or below that. Okay. So for your x's, and we're just going to go ahead and set up all these points in your chart here. They're not hard. You'll see. If you can figure out the starting point in the middle, the rest are easy, and you'll see why. I'm going to start at 0, and I'm just going to tell you. In fact, if you have your calculator out, type sine 0 and tell me what you get. It equals 0.
It's like on the I did. Yeah.
How about the sine of negative pi?
Oh, it's still on 0.
No, you want to use the pi button. It's still on 0. You're not in. Okay, so hit the button that says mode and make sure radians is highlighted. Okay, highlight radians. All right. Now, second quit. Now do it. All right, listen. Listen, Linda. Sine negative pi should give you 0 on your calculator, yes? How do you do negative? Negative is the negative under the 0 there. Is that what you're asking me? Okay, hit mode. And is radians highlighted? Highlight radians. Go to radians and hit enter. Then second quit and now type sine negative pi. Okay. Do the sine of negative pi over 2. How about the sine of pi over 2? There is a pattern. There absolutely is a pattern. Negative pi over 2 is negative 1. 0. Pi over 2 is 1. What do you think pi is going to be? It is indeed 0. What do you think 3 pi over 2 is going to be? Negative 1. What do you think 2 pi is going to be? Do you see the pattern? Indeed, it is a wave graph. And it would continue just this way forever and ever and ever. What do you mean? You talking about symmetry? Oh, it could, yes. No. All right. Let's. What?
It's a pretty graph.
Oh, that's because I forgot to. I think I forgot to make it public. Okay. All right, let's do some analysis here. What is the domain? By the way, if you're on your graph, if you hit zoom 7, if you hit y equals sine x and then do a zoom 7, that's a trig zoom, you'll see the graph and every dash will be a pi over 2 for you. It's pretty cool. If you hit y equals and type sine x and then hit zoom 7, sine graph.
We don't know how to use that.
No, I know. All right. I'm trying to get y'all whereas a lot of ways I'm trying to get you to be able to use your calculators, a lot of other ways I'm trying to get you to be less calculator dependent, because next year in AP Cal you'll have a whole half of the test that you won't be able to use the calculator on. All right. Domain. Negative infinity to infinity. That's okay. Everybody won't take AP Cal.
I will.
How? No, you're not. How about the range?
-1 bracket to infinity.
Wait, what?
-1.
To 1 bracket on each one, right?
Oh, wait,
It's just between those two values all the time. Everybody okay?
Wait, does it have 2 horizontal asymptotes?
Does it have horizontal asymptotes? No, it doesn't have any horizontal asymptotes. It doesn't have any vertical or horizontal asymptotes. It is bounded. How is it bounded? It's bounded above and below. Whoa, Stacy. Is it? Let's think about this for just a second. Remember how we put a negative in for the x? Okay, so you don't know a lot about sine properties, but if I did the sine of negative x, so let's look. If I had the sine of pi, is it the same thing as the sine of negative pi?
Oh, yeah.
Mm-hmm. How about is negative pi over 2 and positive pi over 2? What happens there? Uh-oh. Wait, those are opposite. Opposite. That's right. So if I think about it algebraically, if I plug them in, if I look, 0 is a terrible example because 0 is not positive or negative. But if I look at specific values, I notice that they're opposites, right? And if I were to take this graph and rotate it 180 degrees, it would look exactly the same. So this has odd symmetry. It is continuous for all of its domain, because I could continue to draw it without picking up my pencil. How would you do in the behavior? That's a tough one.
No, because those are always asymptotes.
All right, I know that I'm going to do as x goes to infinity, right? Because that's 1n, as x goes to infinity. My question is, what is the graph doing as you get further and further down? So what I'm going to say, and this is new notation, okay? I'm going to say that y oscillates between -1 and 1. Would you agree with that? The bigger x gets, y just continually oscillates from -1 to 1, -1 to 1, -1 to 1. It just keeps doing that, flipping between them. Does that make sense? How about as x goes to negative infinity? Y still oscillates between -1 and 1. Go okay there? Super okay?
Why are we doing that?
This is a parent graph. We will start, every one that I'm giving you in this packet, we will be manipulating, we will be translating, stretching, shrinking, doing all types of stuff too. And these are the parent graphs you have to know cold. Yeah. We can. Yeah, they're repetitive. So this one. What? No, not this one. We have absolute max, and watch how I do this. At every, what? Where do I have absolute maxes? Pi over 2. This is going to be 5 pi over 2.
Every x pi over 2.
Okay, so I've got, let's think, pi over 2, 5 pi over 2. Where would the next one, how often is it happening? Every what?
Wait, which one are we doing?
How do you get from pi over 2 to 5 pi over 2? 4 over 2, right? 4 over 2 is 2. So at every pi over 2 plus 2k pi's, this is new notation. Let me tell you what this means. This says where k is an integer. Because I'm saying, what I'm telling you is I have maximums that occur every pi over 2 plus 2 pi, but I sub in a value for k. What happens if I put in 1 for k? I end up where? Pi over 2 plus 2 pi, which is
How would you get 5?
Now, where did you get k and where did you get pi over 2? Like, I don't understand about pi over 2.
what is 4 pi over 2 plus that's k means where k is an integer. I'm leaving k in there. K is a what? K is a member of the integer family. K is an integer. What is in quotes is literally what that means. As we get further and further in math, you learn more and more symbolic notation so that by the time you finish, in probably in AP Cal, you should be able to write an entire mathematical sentence with no words. A mathematical sentence.
So are we doing absolute minutes?
So yes, let's look at the mins, okay? The absolute mins, now stay with me, yeah. What's in blue? Okay, so k is a variable, yes? Okay, if I tell you that k is a variable that must be an integer every single time, that means no matter what you plug in, as long as you plug in an integer, every single time you're going to end up at a maximum. If I plug in, let's say I plug in 5 for k. 5's an integer. Do you agree or disagree? A whole number, right? Positive or negative. Every single one of these will equal the max. And the reason is because from one maximum to the next maximum, there is a distance of 2 pi. Do you agree with that? Right? This is a half of a pi, another half, another half, another half. So if I want to, yes. If I want to get to the next one, do you agree that I just simply have to add another 2 pi? Do you agree with that? And if I want to get to the next one, then again with the 2 pi, right? So to get to this one, this point is still a maximum and it's still going to be up here. Do you agree? But to get from where I started, I would have to add 1, 2, 3 2 pi's. Yes. Right.
Is it weird for K to be like that?
Yes.
Wait, so what's the number?
All right, so let's look at the minimums together. Okay, Z, this means integer. Yep. It's a funny looking Z. Yes. This means is a member of. X or K is a member of the integer family. Or K is simply an integer. You can plug any integer in, and as long as you plug in an integer, you're going to end up at a maximum point every single time. K is a variable that I am letting represent an integer. You can't just plug in 0.1 for K because I've defined K as being an integer. You can only plug in integers for K. All right, let's try to do the minimums.
We just have to memorize that. We don't have to understand
If you can memorize, and really you only have to know where it starts if you remember that it's every half pi. Because of the pattern, you can figure out the rest of it. All right, minimums. Where are minimums happening? This time I'm going to start at 3 pi over 2, but the distance between is still 2 pi's. Do you agree? Instead of it starting at pi over 2, it's starting at 3 pi over 2, right? So I'm going to say minimums occur at x equals. I'm going to do 3 pi over 2, but I need to say, I know I could add 2 pi, right? If I did, and maybe this will help you a little bit. If I said 3 pi over 2 plus 2 pi, I would be at another minimum. Do you agree or disagree? If I did that, would I be at another minimum? If I did that, am I at another minimum? Is this the same thing as 1, 2, 3, 2 pi's? Could I, in fact, put any number here as long as it's a whole number and still end up at a minimum? Yes. It's an integer. That's exactly right. At 3 pi over 2 plus 2 pi's, here I am. And I'm still at a minimum. Yes. Okay?
That's what K represents.
Yes.
Okay, when you put it like that, it makes a lot more sense.
Okay, maybe I should put K 2 pi. Does that help you more?
That makes numbers.
We just generally put if we have a number, we usually put the variable after the number and before, but that's okay. Right. But I need to make sure I define K. It's not enough to do that. I need to say that K is an integer. The E means is a member of the family of integers or belongs to the integer family. Yep. Yep. No, I didn't mean to. It's supposed to be, yes, it's supposed to be almost like a C with a line in it. Cosine, you're going to see, is almost a complete replica of this one. It's just shifted a little bit. So we'll be going through this again. So watch. This is number 9. 10. I'm going to set up my graph the exact same way, going by half pi's, -1 to 1. Cosine COS. No. 2 after this. Where am I at? No, we brain braked in the beginning. We didn't start until 15 minutes ago. If you graph it, you will see that it is almost identical. The only difference, and I'm going to take this one out a little bit further so that you can see the whole half pi still. So I'm going to go out. You do not have to put this many on your test. I would do at least -pi/2, 0, and pi/2. You will have the graph, yes. Right. I'm going to stop here on this so that you can see. But if you go on your calculator and you do the cosine of -2 pi, what do you get? Anybody? -2 pi. 1. It's not the same. It's flipped up. It's switched up. How about, oh, we didn't do zeros on the other, y'all.
Well, I was going to ask you about those because how do you say there's zeros go on forever? Oh, it's probably another day.
What happened?
It's another it's weird.
What happens at the dang zeros? It's another dang interval. All right. What happens here? Where are the zeros happening? Every whole pi. So this time I'm going to say x equals, this one's easier, x equals k pi, where k is an integer. If you put x pi, what happens is you start getting your x's mixed up with your x and your coordinate, and that's why. So we say k pi and we let k be an integer. Okay, so you're going to define your k at the beginning of your test and say every time I use a k, k is an integer. Okay. You could. All right, let's come back over here to our cosine graph. Every k pi is zeros. Thank you. All right, what do you get at -3 pi over 2? -3 pi over 2. I bet you could guess. 0. How about -pi? How about -pi over 2? How about 0? All right, so I'm going to go ahead and graph these. And you see the pattern is very easy to pick up on. And in fact, it looks very similar. Very, very, very similar to the sine graph. The only difference is it's peaking at 0 instead of a 0 at 0. continuous, yes or no? I'm sorry.
Where would you even learn this stuff? Is this like advanced geometry or like
No, this is
calculus?
definitely huge pre-cal. This is in fact we used to have an algebra 3 class and it was focused mainly on trig and that kind of stuff. We used to have a trig class too.
Oh yeah, true. They haven't. They did.
This is trig. This is trig. All right. This is continuous. Yes. What do you think about the symmetry? Very symmetrical. So what would that be? Even.
How's the other one on?
There's a bug on the floor. If you rotated it 180 degrees, it'd look exactly the same. The other one. You said the other one. This one splits down the middle. It's symmetric.
Oh, okay. Wait, I think I have it. Oh, yeah, the other. Okay, I see it. I see it.
All right. Domain. Range. Zeros. K pi instead of 2K pi. Because look, it crosses here, yes, and then it crosses here. How much space is between these two zeros? It's not 2 pi's anymore, it's just one whole pi. So this time, my zeros happen at pi over 2. Oh, that was on the zeros. I'm thinking the maxes and mins. I'm sorry, yeah. Plus K pi. K is an integer. Okay. C. I don't think it's going to be Monday. No, I think it's going to be Tuesday. Not for the sine and cosine. You don't know enough about it yet to do that. All right, maximums, where are they happening? All right, it happened at 0. And then it happened again at 2 pi, yes? And then it happened again at 4 pi. So it's happening, right? But I need a starting point. And that's the only difference in this. Y'all look at the two of them. It just slid over a half a pi. That's all it did. So my starting point is going to be a little different. So at x equals, what do you want to say? I could say 0, but maybe I should move over to the first one. Let's say 2 pi. X equals 2 pi plus what? K 2 pi's, where k is an integer. Is it making a little more sense now? Okay. You try the minimums. Find the first one, and you know they're separated by 2 pi each time. It's just my starting point. Are y'all okay? In behavior is exactly the same as the in behavior for sine, because as x approaches infinity, yes. And actually here, I'm going to say as x approaches positive or negative infinity, because I'm tired of writing it. Yes.
It says K 2 pi. That's like how much space in between the two.
Wait, so should we write positive and negative infinity on test?
Yes.
Can we not leave it? Let's not do it.
We gotta stop here. Yeah, I need to go to test. I have to go to test.
Tangent is not one of your 12.
Are the next two a little easier?
That was the worst job I've ever seen.
The last two are easier than these two. All right, let's run through these last two quickly. You should have seen, I'll do the hardest one first.
Wait, can you go over the man?
Every pi plus k times 2 pi. All right. Number k 2 pi. Yes, the same. This is the step function. If you had me first semester, we did this. If you had me second semester, I don't remember doing it, but that doesn't mean we did not. We're not going to do the third one just yet. It's a little bit harder, and it's kind of a combination of those two. I think I'm going to wait until we get to the unit circle and show you that. All right, 11, the step function. Also known as the greatest integer function. It takes every decimal and it rounds it down to the nearest whole number. Okay, are y'all with me there? So 1.1 would be 1. Okay, are y'all with me on that? And let me make sure your book is going down and not up. Oh, that's calculus. Yes, it's called INT. What? What? It rounds them down to the nearest whole number.
Round them down.
I'm checking your book to make sure. Some books do what they call the ceiling, and some books do what they call the floor. Yeah, this one rounds down. It should be in math. It should be math, number, or somewhere in there. I'm not real sure where it is. Yeah, we have enrichment. I did everything in enrichment already, so I have an extra 20 minutes, y'all. All right. This rounds down to the nearest integer, okay, but it includes the low value of the integer. So what I mean by that, we'll just go by 1. 0 is still 0. 1 is still 1. 2 is still 2, and so on.
High School. Please stand and join me for the Pledge of Allegiance. I pledge allegiance to the flag
of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Please be seated for a moment of silence. Thank you. Camden will host Lugoff Elgin tonight at Zip Stadium. Advance tickets are $7 and may be purchased
down to the nearest integer. If I am at 1/2, right, x equals 1/2, what would the nearest integer be? Down.
So it looks like 7.9 or down because it's 0.5.
But this function rounds everything down. That's what this does, is it rounds it. 0.99, still 0. It rounds it down until you get to that integer, at which point it becomes the integer itself. So this would be an open dot here. It does not include 1, but it includes everything in between. Yes, so this one would be an open dot here. You have to put the open dots. Sometimes this is called a step function because if you look, it looks like steps. But the concept itself is fairly easy. At the value of the integer itself, it is that integer. But everything in between, it rounds down, it goes backwards until you get to the next integer. This is what you will need to put for your graph on the test. This is what it needs to look like. Yes, yes. Something just to show that you understand what's going on.
Okay, wait. Okay, so you would plot a low. Why are your circles? So you'd plot 1/2.
So I'm just showing you that at these points, it's rounding down to. Now, as far as this goes, you can put whatever points in here help you to understand. At 1, it's 1. At 2, it's 2. But everything in between, if I go to 2.2, that's rounding back down to 2. Okay?
So how would you plot those? I'm saying, like,
So,
go to 2.2.
so what I would do is I would put points at 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and so on. And then you know that on the other end, you've got a non-inclusive point, and then fill in between. Okay?
So this right here, okay, so just plot the original point and fill in between.
Yep.
How do we know what the original point is? Take up?
Every integer.
Oh, yeah. Can I put
These are integers. Yes, 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 yes. All right, let's do the analysis on it quickly. Yeah. Because it always rounds down. If it's 0.99999, if it's 3.9999999, it's going to round down to 3. This makes everything round down. Well, look, at 0.99999, it's still here on 0. At 1.999, which is almost at 2, it's still at 1. It doesn't jump up to 2 until I get to 2. This circle means it can't be that point. It's like doing a parenthesis, and this is going from 1 to 2, but doesn't include 2. No.
Okay, wait, okay.
Okay?
So we don't have to actually plot a point or the, so you have like 1.99 or something, you don't actually plot that point.
No, it's just, right, exactly. The line, all of this is a culmination of all those little teeny points.
Okay, so I was asking.
Okay? All right, what is the domain? Yes. Can you plug any value in for x? Yes. Does it matter if it's a decimal, a fraction, a positive, a negative? Nothing matters, right? What's restricted? The y. Okay, here we go.
How do you know the y? Because it can only be a whole.
Look, it can only be, that's exactly right. You said it exactly right. So K, what is K?
I hate it. Yeah, right.
It includes K. Okay. Or you can say the range is all integers if you would rather write it out. Okay. How about, is it continuous? It's the jump one. Continuous. No, it's a jump. It's a jump. Because it says continuous, why or why not? So I want to make sure I give it to you the same way you're going to be asked it. What is there? I don't know.
So how will we plug this into our graph? We do have to graph it. We can't. We're not. We don't. We can't use our graph.
I don't finish grading them.
You did this.
I haven't.
Oh, thank God. Yeah, for my symmetry, I just know it. I know that by that face, it's bad.
No, I'm done with everybody's first page, and I'm halfway done with everybody's last part. So far, they're good. I mean, it's out of 60 points. It's not out of 100 points. Because I don't want to be like, oh, this is Brett's test. I don't like Brett. I'm going to take off extra points for him. I don't like to look at names whenever I grade. I don't look at that. But there were a lot of people who got the entire first page right. A lot. All right, let's finish this quickly. Does it have symmetry? I would argue either way with this. I'm going to go no. That's my argument with that too.
I didn't think they could have symmetry there.
I would say no, they can, but I would say no here because Brett's absolutely right. If you did it 180 degrees, the included point would be on the non-included point and vice versa. And I don't think that would work. What are we missing? Max min? Yeah. Max min? Nope. Bounded? Nope. What are we missing? It does. We won't do in behavior on this one. We won't do in behavior on this one.